marine science scientists would like to share on how present-day climate change has impacted our ocean marine productivity and how future climate change will be affecting the productivity in the future. Marine productivity is the engine of the sea. Marine productivity refers to the rate at which organic matter is created in the ocean, primarily through photosynthesis by microscopic marine plants called phytoplankton. Phytoplankton is a photosynthetic powerhouse. Imagine a vast underwater meadow not of grasses, but of single-cell algae. That's essentially what phytoplankton are. These diverse microscopic organisms come in various shapes and sizes, but they all share a key characteristic, which they are photoalgophiles. This means they can make their own food using sunlight, carbon dioxide, and water through photosynthesis. Factors affecting ocean productivity are light, nutrients, and more. Several factors influence how productive an ocean region is. Sunlight is essential for photosynthesis, so areas with more sunlight tend to be more productive. Nutrients such as nitrogen and phosphorus are also crucial for phytoplankton growth. Upwelling, a process that brings nutrient-rich deep water to the surface, can create highly productive zones like the California current. Threats to ocean productivity are climate change and pollution. Ocean productivity is not static. It can be affected by natural fluctuation and human activities. Climate change, for example, can alter ocean temperature and circulation patterns.
Hi, I am Prof. Lee, one of the scientists from G2. I would like to focus on how the present-day climate change has impacted our ocean's marine productivity. Nowadays, worldwide climate change is increasingly affecting our ocean's marine productivity. We have investigated the impact of ocean warming on marine organisms, particularly invertebrates, fish, coral, algae, phytoplankton, and zooplankton. The majority of these studies analyze the effects of ocean warming on the physiology, life cycles, and survival of these organisms. Out of the evaluated studies, 78.8% reported negative impacts, while 20.1% reported positive effects, and 1.1% observed species with neutral responses to the impacts of ocean warming. As temperature rises, tropical organisms will continue migrating toward higher latitudes, while cold water species will continue relocating towards deeper water or shifting towards the poles to cope with the changing conditions. These changes could result in complex and unexpected interaction within ecosystems. Species with a restricted thermal range, limited dispersal abilities, and slow adaptation to rising temperature are vulnerable to adverse effects, such as reduced foraging and spawning areas, decreased population connectivity, and a higher risk of extinction. This group includes various species such as tropical fish, coral reef fish, reef-building coral, snail, mussel, mangroves, seagrass, polar bear, and other cold-blooded species. In contrast, species with higher thermal tolerance, adaptability, and flexibility to rapid changes in ocean temperature can experience positive effects from ocean warming, enhancing their reproductive and dispersal strategies, distribution, and survival. This group includes several species such as jellyfish, sponges, tuna, seagrass, algae, fish, and even reptiles, marine mammals, seabirds, and penguins.
The effect of climate change and global warming due to pollution and release of carbon dioxide gas is increasing in being found by the country's fishing industry, which has recorded a decline in the number of cases over the past few years. As the data for the period 2020-2022, the Department of Fisheries Malaysia said there is a consistent decrease from year to year for the period in question, which directly reflects the threat to the country's food security. In 2020, a landing of 1.38 million metric tons of seafood is recorded, declining to 1.2 million of seafood is recorded, and 1.1 million metric tons the following year. One of the causes is the increase in sea acidity, which makes the seawater warmer, prompting groups of pelagic fish such as pufferfish and driftwood to move to areas where the water is cooler, said Director General of Fisheries Dato' Alan Hussein in an interview with Bernama Zahid. The issue, if left unchecked, not only threatens the country's food supply chain, but more critically has the potential to close the source surge of more than 100,000 full-time fishermen registered in the country. Due to the lack of seafood in their usual area, fishermen will expand their fishing activities to other areas, thus increasing competition with existing fishermen in the area concerned. This is one of the reasons why some of our fishermen report that their catch is decreasing, he said. According to him, the increase in sea acidity also affects fish breeding habitats, which are areas of coral reefs that are reported to be bleaching, directly affecting the fish population in one area. The problem of increasing temperature and sea acidity not only has a bad impact on sea fishermen, but also on key fish farms who are facing threats, including with algae explosions like the one that happened in Penang and Perak recently. The incident had a significant economic impact on the fish farmers in the cages involved when their fish died due to lack of dissolved oxygen in the water due to the algae cover.
Hi, I'm Professor Novel. Ocean and coastal ecosystem and their resident species are under increasing pressure from a multitude of climate-induced variables. One of the most significant focuses is the future changes in marine biomass and primary productivity. SSP 1-2.6 and SSP 5-8.5 share socio-economic pathway scenario developed by the IPCC were used to model potential future changes of greenhouse gas emissions and their impact on the Earth climate. Next, spatial patterns of stimulated change by 2090 to 2099 are calculated for SSP 1-2.6 and 1995 to 2014 for SSP 5-8.5. As the figure shows, the biomass anomaly in surface phytoplankton, zooplankton, animals, and sea floor planktons decreased for both SSP, especially for SSP 5-8.5. By looking to result of SSP 1-2.6 indicates that the biomass anomaly of phytoplankton only reduced around 0 to 10%, zooplankton will decrease around 10 to 20%, animals reduce around 10 to 20%. Meanwhile, sea floor planktons in future will be highly reduced globally, around 30 to 40%, but it shows an increase of 10 to 20% at South-Pacific Ocean region.
Hi, I'm Prof. Fadila. Have you heard about the ocean life that is going to be kept up by 2100? By using the latest software, which is CMIP6, the global net primary production is projected to decline by 2080s until 2099, relative to 2006 until 2015 by about 5%. This was different from CMIP5 model that predicted the faster rate of declining of global net primary production. However, different models will show various results and future scenarios. Multi-model mean changes in primary production shows the similar patterns of large declines in the North Atlantic and the Western Equatorial Pacific. Meanwhile, in the higher latitude shows the constant increase of primary production in CMIP5 and CMIP6 by 2100s. The subtropical North Pacific and Indian Ocean shows a consistent net primary production decline in CMIP5 projection. By using CMIP6 projection, the regional decline shows a less robust and reduction in magnitude of both regions. By referring to the IPCC assessment of ocean primary production and carbon flux, we were able to summarize it and projected the possible impact for the future. From SROCC, the net primary production in the open ocean was very likely to decline by 4 until 11% by 2018-2081 until 2100 across CMIP5 models for RCP 8.5. But this projection shows low confidence level due to the limited evidence from observation. The net primary production of tropical ocean was likely to decline by 7 until 16% for RCP 8.5 with medium confidence. Besides, the projected export production can be larger than global primary production in the open ocean due to the relation with net primary production changes and shift in the food web that modulate the transfer efficiency. The changing of nutrient supplies can be constrained by interior ocean nutrient and oxygen level with medium confidence in global projection based on CMIP5. From WGIAR6 Chapter 2.5, the export flux is projected to be declined by 1 until 12% of export flux by 2100 using CMIP5 under RCP 8.5. The similar value is predicted in 18 CMIP6 model with declining of 2.5% until 21.5% by 2100 under RCP 8.5 scenario. These changes vary widely between models due to the different parameterization of particles formation, mineralization, and plankton community structure.
As we confront the challenges posed by climate change to our oceans' productivity, it's imperative that we consider both mitigation and adaptation strategies that delve into some recommendations. Firstly, addressing the root cause is crucial. Mitigation strategies aim to reduce the human-induced stresses on our oceans. According to the IPCC report, cutting down greenhouse gas emissions is paramount. Government, industries, and individuals must collectively commit to adopting sustainable practices and transitioning in cleaner energy sources. A major aspect of mitigation is the sustainable management of fisheries. Overfishing exacerbates the vulnerability of marine ecosystems. Implementing and enforcing regulations that promote sustainable fishing practices, such as setting catch limits and protecting breeding grounds, are important steps. In conclusion, our collective action today will shape the future of our oceans. By embracing a combination of mitigation and adaptation strategies, promoting global cooperation and fostering innovation, we can strive toward a more sustainable and resilient marine marine environments. Let's work together to ensure that future generations can continue to benefit from the incredible productivity and diversity of our oceans. Thank you.